So good afternoon, everyone. Welcome to this third installment of the NITheCS Mini-school on solitons in physics and mathematics, introduction to soliton and solitary waves. And sorry, I should introduce myself. My name is Francesco Petruccione. I'm the interim director of NITheCS. And this afternoon, I have the pleasure to introduce to you the third speaker in the lecture series of this month, Professor Herbert Weigel. Professor Weigel studied or did his PhD in Siegen, at the University of Siegen in Germany, and spent then a couple of postdocs in the US, in France, back in Germany, where he completed his habilitation at the University of Tübingen, after which he was awarded a very prestigious fellowship from the German Science Foundation called the Heisenberg Fellowship, which sounds really appropriate. So well done for that, Herbert. That's really a prestigious thing. And with that fellowship, he spent some time at MIT and back in Tübingen, after which he became a professor at the University of Siegen. And in 2000, I don't remember, in 2000 and something, he joined Stellenbosch University, 2009. So, okay. and he's been ever since in Stellenbosch. Yeah? And I won't describe to you the research of Professor Weigel, because he will speak about some of his favorite topics, I guess, just now. Yeah. So Herbert, we are very glad that you're with us. You are welcome to share the screen if you're planning to show up as a presentation. And while you do that, I will just remind the participants to please use the Q&A facility to ask questions, and maybe at the end of the talk, raise your hand and we can give you the right to speak. Yeah? And Daniel and Professor Malomed will help me at the end of the talk moderate the questions. Yeah. So Herbert, please, it's your show. Okay. Welcome to start.
Yeah, thanks, Francesco, for the nice introduction and for putting me on the show. So I think I share the screen and then go to my PDF and try to see where we take it from there. Okay. Okay, so desktop, I guess that should now work. Okay, I hope you can see the can you see?
Not yet.
Okay, so maybe I thought okay, I have to press the share button. Okay, so that's
that usually helps.
Yeah, okay. So now it should go better.
Now we see your screensaver. We don't see your presentation yet.
Okay, so then I went to the wrong screen. Okay,
possibly.
One more try.
It's a very nice photo. Yeah.
Okay, so where is stop share? Okay, so that's this thing in here. Try it again. Okay, so why does this thing not show up here? Advanced. No. Okay, I think I may have to move this to the proper desktop and go to that desktop. Okay. Does it work now?
We still see only your screensaver.
That's okay. So
it looks like maybe you need to unmirror or mirror two screens or something like that.
No, everything has gone. Completely confused now. I can't even go back to the original page. Maybe that's now here. No. Probably I have to log out again and log in again, because I can't even find the
You know,
Okay,
you can when you click on the share menu, you have the choice of choosing the desktop or an application usually. If you choose the desktop, then you can open it on
but I actually have 4 desktops here on my computer and it shows the wrong one. That's the problem. Okay, so but I now don't even get the main page from okay, so this got back. Stop share for the time being. Okay. Okay. Desktop 1, okay, so maybe I've moved this thing here to desktop 1. Then it could work. Oh no, maybe this one in here. Okay, how's now?
Okay, now we are in business.
We're in business. Okay.
Yeah.
Okay, so yeah, now I've also got it on full screen. Okay, so thanks again, and sorry for this 3-4 minutes that it took to figure out. It's the first
sorry,
time
Herbert. Now you press full screen and the screen turned black.
Oh, that.
We could see it before the full screen.
Okay.
Now we can see. Perfect. Just leave it like that.
Leave it like, maybe I go to full screen mode. I went to presentation mode and that doesn't work. So does it work now?
Oh, it looks like it. Yeah.
Okay, so there seems to be a difference between full screen and presentation. Okay, so
okay. I don't know. Excellent. But thank you very much. So now we can start.
Yeah. Okay. So yes, finally. So I'm going to talk a little bit about chiral soliton models for baryons, and well, I did not make it up as a research talk. So since it's part of a presentation series at Mini-school, I try to keep it with that. Okay. So and yes, and also will not have that many references. Actually, none in the talk except of one, because most of the stuff is taken from the book that I wrote about 10 years ago or even longer ago, published by Springer. Yeah, so since if I want to be explicit, I had probably to give 100 references in there, but you will all find relevant citations in that book. And I checked, actually, Stellenbosch University at least has 1 copy of that, and I have another one here in my office. Okay, so let me briefly outline my talk. And so I will actually, the first 2 sections, or maybe even the first 3 sections, are not really about a particular soliton at all. They are more devoted to the topic that, to the question of why we actually should look at solitons in particle physics at all. So I will briefly review some aspects of particle physics and the main interaction that we are looking at, that is quantum chromodynamics, but I will generalize that in the sense of Witten's work to many color degrees of freedom. We will find out or argue that there is actually something like an effective meson theory that should be equivalent to QCD, and we will try to model that effective meson theory by mocking up the main symmetry of QCD at low energy, which is the chiral symmetry. And then I will actually go to the square model, or the skyrmion, the first such soliton that can be used to describe a particular set of particles that are subject to the quantum chromodynamic interaction. So in contrast to previous talks in this series here, I will not solve for many different solitons, but I will essentially just take one soliton and see what can we do with that object. Okay, so the skyrmion by itself will not yet have good quantum numbers to describe hadrons, in particular baryons, and we have to quantize the skyrmions and generate states that have good spin and also an isospin quantum numbers, and that will be the main topic of, or the main application of the skyrmion. And I will also briefly discuss a little bit about meson-baryon scattering that can be done in this model, and describe extension of the Square model, in particular with respect to vector meson degrees of freedom, to refine the predictions from the model. Before actually doing that, let me go a little bit into the history of the skyrmion or the chiral soliton models. So actually, Skyrm developed that model in the early 60s of the last century as a model for composite particles. And he actually did that already before Gell-Mann introduced the notion of quarks. Okay, so that actually is older than the quark model. Okay, so it actually got really popular only in the late 70s when Witten considered QCD, that by now was established as the model or as the theory underlying strong interactions, that this QCD theory could be generalized to a large number of color degrees of freedom. And in that limit, it turns out that baryons can be considered or as solitons in an effective meson theory. And a few years later, with two of his collaborators, actually with a graduate student and his wife, Witten then used Skyrmion to actually show us that one really can do something with that model. And thereafter, there were many of soliton models and projects on that model to describe and predict baryon properties. In the 90s, it was but famous again because it was able to explain the so-called proton spin puzzle, because there were by now experiments that showed that the quark contribution to the a particular current, which in the quark model is identical to the spin, was much smaller than the spin itself. Okay. And in the early 2000s, there was the famous soliton approach to the infamous pentaquarks. Okay, so these are some exotic particles. I will briefly mention them in talk that cannot be built out of 3 quarks, but are nevertheless baryons. And nowadays, there are still popular skyrmions in the context of condensed matter in 2 space dimensions, where they are used to describe the magnetization of solids. And I will not talk about that because this is not really a particle physics subject. Okay, so aspects of particle physics. So we are all familiar with electromagnetism. So we have electrons and photons, the quanta of the electromagnetic field. They build together quantum electrodynamics, and it's probably one of the most successful theories in physics. Just think of the anomalous magnetic moment of the electron, which is predicted to whatever 8 significant degrees of freedom in QED. But that's not the end of all our particles, it's just the beginning. Okay, so the first thing that you will recognize is that you can duplicate these electrons. So they have syllables called muons and taus, which are also leptons. So they essentially have the same quantum numbers, but different masses, much larger masses than the electrons. And you can also duplicate the photons into the W plus minus and the electrically neutral set. And they play a similar role like the photon in electrodynamics. So the gauge bosons for the weak interaction or the weak nuclear interaction, and put together with the photon, they give you electroweak interaction and all the leptons in there. And these leptons are also accompanied by neutrons. So, okay, so and this is actually still a quantum field theory, the weak electroweak interaction, which can be nicely treated in perturbation theory, well, to some extent nicely. There are further copies of electrons, which are then subject to the strong interactions. So they are called quarks. Well, they're not only copies of the electrons, they're also to be understood as copies of the neutrinos. And there are 6 of them from up to down to top. And these guys are called quarks. And the analog of the photon in that theory, that are the gluons, and that theory is then the quantum chromodynamics. Okay, so and that is supposed to describe the strong interaction, the nuclear strong interaction. But there is a major difference between QCD and QED, and that is that QCD gluons, they self-interact. Okay, so meaning that the gluons themselves have the charges that occur in quantum chromodynamics, while in QED, the photon is electrically neutral. And this gluon self-interaction causes the perturbative treatment that we have been using so far in the other theories not to be applicable. Okay, so it's trying to do that is somewhere between difficult and impossible. Okay, so that is, so to speak, the picture of the content of the standard model of particle physics, where we now have electrodynamics, the weak theory, and quantum chromodynamics. So I start off with the electron and the photon, which is called gamma. Now we also have the W and the Z for the electroweak interaction, and the gluon for the strong interaction. So these are the force carriers. And then we have these copies of the electron, each have a neutrino, and we have the quarks in there that are the matter fields for the strong interaction. Okay, so in that model, let's have a look at the elementary beta decay, and that's already known since whatever Pauli, okay, because he introduced the neutrino. So, but on this elementary level, where we look at quarks and electrons and neutrinos, it's a transition from the down quark to the up quark, and then we and that emission goes together with a W minus that's exchanged, and this W minus then decays in electron and an anti-electron neutrino. But of course, the observation doesn't refer to quarks. The observation refers to neutrons and betas and protons, which is then the so-called neutron beta decay. And the reason that we can nevertheless describe that on an elementary level is that these neutrons and protons, they are not elementary particles. They are subatomic particles, but they have a quark substructure, in a sense that the neutron is built out of an up and two down quarks, and the proton is built out of two ups and one down. And then the beta decay is simply describe the transition of this up-down into this down quark into an up quark. Okay, so and as you see, these subatomic particles, they are built from quarks and eventually also from gluons. And these subatomic particles that are all of them that are built out of quarks and gluons, they are called hadrons. And that cannot be the full story because these quarks by themselves are fermions, but so are the proton and the neutron. And we need an additional quantum number to make these states fully antisymmetric, because they should, of course, be subject to the Fermi-Dirac statistics. And some of these states, if you look at the UUD or others, UUU or triple U's, their wave function would be completely symmetric under the exchange of any of the two composites, but that cannot be true. And there is an additional quantum number, which is called color. And in that quantum number, these wave functions are fully antisymmetric, and therefore getting us back to the Pauli principle. Okay, and the quarks carry color, but also the gluons carry color. And there are actually, in the real world, we have three different colors in order that we can build objects built out of three quarks. But we can also generalize that value of colors to an arbitrary value NC. And then the gluons, they actually have NC squared minus one color, so they are somehow sitting in the adjoint representation of the group theory. Okay, but I don't want to go too deep into group theory in here. So we can almost understand that as, for example, one component being red bar, but you could also have it at red green bar, and so on and so forth. And the color is actually the charge carrier. And as the gluons carry this color, they have this self-interaction. And if you do a running coupling constant and the group running renormalizing group calculation, you will actually find that this coupling constant becomes large at low energies. And that makes an perturbative treatment to investigate the properties or static properties of hadrons more or less impossible. Okay, it has on the other hand, one advantage: it becomes small at high energy, and that's what we call this coupling becomes small at high energy, and that's what we call asymptotic freedom. Okay, so and it actually allows us to make predictions and relations or established relations between different high energy observables of hadrons. Okay, so in addition, we have this confinement conjecture. So this is still one of these $1 million questions, that is at this point still only a conjecture, but it says that we only can observe color neutral combinations of quarks and gluons. Okay, so in principle, this color neutral is a group theoretical statement, but we can also describe it here very heuristically with these really three colors, for example. So we would have an object that has a color or is a composite of a color and its anti-color. That would be color neutral, so it would be white. Okay, so those objects which are quark anti-quark substructure, we call them mesons. Okay, so and these are objects with integer spin. Has to be so because if we couple two half integers, we get integer spins. Okay, so and another set of hadrons that we can make color neutral is if we put together all possible colors. So for example, red, blue, and green, that also makes white. And this gives us hadrons with half integer spin because we couple three half integer spins together, and these are the baryons. So the most popular, of course, being the proton and the neutron, but there are plenty of them, like for example, an isospin excitation of the proton and neutron, which is the delta. Okay, so as I already said, we cannot really do much about the calculations of QCD at low energies, except maybe lattice, but that's something we have been saying 30, 40 years ago, and we're still not really satisfied with those results. And therefore, we have to invent some models. And of course, we want to invent models that are motivated or at best even be derived from quantum chromodynamics. And with these models, we then will try to describe hadron properties like their masses, their size, magnetic moments, form factors, you name it. Okay, so how do we find such a model? And that goes back to Witten, who generalized quantum chromodynamics from 3 colors to infinitely many. And actually, Witten did that for baryons, even before Tufte did that for mesons. Okay, so we will simply count multiplicities of certain Feynman diagrams that may be relevant for the structure of hadrons. And then only consider those diagrams which have the highest multiplicity in terms of their color arrangements. And the idea is a graphical solution to that problem. It's called the double line notation. And we just want to get the combinatorics of various Feynman diagrams. So we have a quark with a certain color, let's call it A, and we have an anti-quark with an anti-color, call it B bar. Okay. And as I already said, that the gluons carry NC squared minus 1 colors, but of course, if NC is large, that minus 1 can be safely ignored. And let's therefore say that a gluon has a color A and an anti-color B, or B bar, and we just give the double line notation where for the combinatorics, we equate the gluon line with 2 quark lines, or more precisely with a quark line and an anti-quark line. The simple such application for that would be the gluon self-energy. And so you have a gluon coming in, a gluon loop. I said it's self-interaction. So we have some vertex where 3 gluons interact and they return to a single gluon in the final state. And if we look at that, we had initially prescribed colors A and B bar. Of course, they have to come out. But in that double line notation from the intermediate quark loop, we get an additional color degree of freedom that is not fixed when we fix the initial or the final color states. And therefore, this C and C bar can take any of the NC possible values. Okay, so that means at face value, this diagram in the multiplicity of NC would be of the order NC to the power of 1. So at that point, the theory is not really well defined because we want to have this gluon self-energy to have a smooth limit. Okay, so and what we need to do to achieve that is to say that we also have to give the gluon self-interaction constant an NC dependence. Okay, so we have two such vertices. So this diagram is quadratic in that self-interaction coupling constant. And if we say that this self-interaction scales like 1 over the square root of NC, together with this NC factor from the combinatorics, that diagram is of order 1. And then you can go through many, many, many diagrams. And let me just go to 2 examples, 2 which are also contributing to the gluon self-energy. So one which is called a planar diagram. So I've added 2 additional internal gluon lines that are also interact. Okay, and that gives it the name planar, because they are matching in one point, and you can draw that diagram in a single plane. I want to compare it to a non-planar diagram where I omit that interaction in the middle, and then one gluon would have to pass on top of the other, and you cannot draw it in a single plane, and then therefore these are called non-planar diagrams. Okay, so if you introduce the double line notation, you will see actually that there are 4 independent color loops for the top diagram, but if you follow the color loop in the bottom diagram, there's only one line that's actually free. It's only a single line in there. Okay, so and then we have to multiply that by the NC scaling of the coupling constant, and we should also mention that the coupling constant for the 3 gluon vertex is just G, but for the 4 gluon vertex it's actually G squared. And if you put this together, you will actually see that the top line is of order NC to the power of 0. So that's what we established earlier. But the lower one, which is non-planar, is actually suppressed by 2 orders in NC counting. Okay, so the major findings is that the internal lines are just gluons. There are no quark inside. They are suppressed. All lines are in a plane. That's what I argued above. All intermediate states are actually colorless. Okay, we should use Skotowski's rule and cut it in here. All color lines are written in terms of a single trace. I didn't introduce quarks in there, but you can draw quarks at the edges of all the diagrams, and you will see that these diagrams are of the order NC. And they can use, for example, to describe mesons once you add creation and annihilation operators, or insert them into those lines at the edges. And a 2 meson diagram is of order NC and has 2 of these annihilation or creation operators. So the operators have to scale like square root of NC. You will also find that the meson masses have a finite limit as NC goes to 0. And for resonance, it's actually 0. And if you add additional creation or annihilation operators on these edges, each of them gives you a factor NC, but the diagram by itself is of the order NC, no matter how many operators you insert, and therefore the corresponding coupling constant in front of it has to scale like NC to the power of n-2, and that's where the word effective theory comes, or the effective theory comes into the game. If you want to consider scattering, you need 2 annihilation and 2 creation operators in there, so n is equal to 4, and the corresponding coupling constant scales like 1 over NC. So that's why this meson theory is weakly interacting, so the interaction decreases with NC. So these are the mesons. What about the baryons? Well, we would have NC constituent quarks, and well, perturbative treatment or just combinatorics, that just fails. But what you can do is you write down at least non-relativistic Hamilton operator in there and perform a Hartree calculation in there, and you will actually see that with this Hartree approximation, where the wave function is just a product of all walk wave functions, NC scales out. Okay, so meaning that the single quark wave functions do not scale with NC, or at least have a smooth limit, and each of these quarks contributes an epsilon into there, and this epsilon also has a smooth limit. So in that case, or for that reason, we argue that the baryon mass is actually of order NC, okay, because all terms here in that right-hand side of the variational principle scale like NC. But NC was the inverse of the coupling constant for the effective meson theory. Okay, so that's another major result of these observations. You can go on to similar considerations for the radii. They turn out to be of the order NC to the power of 0. Similarly, you can write down a Hartree wave function for the meson baryon interaction, and you will see that the wave function or the Schrödinger equation for the mesonic piece in there doesn't have any NC in there. So therefore, all information about meson-baryon interaction, in particular in all the scattering data, they are of the order of 0th order in the effective coupling constant. Okay, so let's now first really come to solitons, so the very first one in this talk, and that's the kink. Well, this is a very simple Lagrangian, and it has a static solution in 1+1 dimension, just a tanh in there. And the coupling constant here is the lambda. That's the coefficient of the 4th order term in the potential. Okay. And if you do the calculation and calculate the energy associated with that kink, you will find that the energy is inversely proportional to that coupling constant. So that's exactly what we've seen from large NC QCD. We have a coupling constant, and the masses of the baryons are inversely proportional to that. And the other properties also match. If you look at the radius of the kink, it doesn't contain the coupling constant. The scattering phase shift doesn't contain the coupling constant either. Okay, so and that's when Witten conjectured that baryons actually should emerge as solitons in an effective theory of weakly interacting mesons. So weakly, again, just as a reminder, it says that the coupling strength decreases with the number of colors. So what is this effective meson theory? Well, we really want to construct that theory as a meson theory and then make predictions for the baryons using the soliton picture. Okay, so I also took the effort to write down the QCD Lagrangian. As simple as it is, it fits on a stamp, but okay, so 50 years of research have not really finished now. There are two. Okay, so the quarks in here that show up in here, they come in different flavors. We had already the up, down, and so on, the number of quarks in there. So let me just generalize that to NF, which is the number of flavors. I don't really want to go to 6. Mostly, I'm just talking about 2 and 3. Okay, so there's an additional symmetry. Well, if the mass matrix in here, okay, you can't see it in here, so that contains the masses of the various quarks. If it's proportional to the unit matrix, then there is a conserved vector current. So that's an Noether current, and its divergence is 0. And if the mass were actually 0, then there is an additional axial current, which is also conserved, also has d mu, a mu equal to 0. And usually one writes these terms in terms of left-handed and right-handed quark fields. And this a mu has, in addition to the standard vector current, an additional gamma 5 in there, so it's a pseudo vector. So these two approximations, they are more or less valid for the up and down quarks because they are so small, and to a lesser extent, they are also true for the strange quark. And so the flavor symmetry that we have in here is therefore something like an SU2 for the left-handed quarks and an SU2 for the right-handed quarks. In addition, there is a U1 for associated with a vector transformation. That's nothing else but the baryon number current. And then there is an axial U1 in there, which unfortunately is anomalous in the sense that it's not conserved due to quantum corrections. Okay, so if we want to build up a theory, we want to build it up such that these symmetries are represented. Okay. Okay, so then let me look at the meson mass spectrum, and you see that, well, if this symmetry really was realized, we should see more or less degenerate scalar and pseudoscalar mesons, but that's not what we're seeing. So we're seeing a number of pseudoscalar mesons, for example, the O minus, most importantly, the pion, it's actually almost massless, and the kaons and their rho and omegas in there On the other hand, for the scalars, there are just a few broad resonances. Okay, so this is a completely different picture. There is nothing like a degeneracy between the left and the right hand side. Okay, so and that brings into the spontaneous symmetry, or the idea of spontaneous symmetry break, chiral symmetry breaking, in a sense that there should be something like a quark condensate, meaning that the vacuum in QCD is not zero, but there is an expectation value of Q bar, and that's non-zero. And then once there is something like a non-zero vacuum expectation value, you should see massless modes, the so-called Goldstone bosons, or almost massless modes, and that you get by performing the symmetry that is broken onto the condensate, and that brings into the game pseudoscalar fields. Pseudoscalars, see it again, there's a gamma 5 sitting in there. Okay, well, almost broken is the pion would be massless if the chiral symmetry was exact, meaning if M was indeed zero, then the pion indeed would be sitting here at zero and would be a real Goldstone boson. But it has a small, tiny mass, but let's forget about that mass term. And if that's the case, the simplest effective meson theory should not have a mass term, so it should only have derivatives of that field representing the Goldstone boson. Okay, so I think I should go a little bit quicker. Let me forget about the details of this NJA model, which actually is a way to really go from a fermion self-interaction to a meson self-interaction by the method of bosonization. And the only thing I want to take from there is this, if you have a transformation in SU N on the left-handed and a separate one on the right-handed quarks, that turns over into a transformation law for the meson fields in that effective theory. Okay, and the fact that the vacuum expectation value of the quark condensate is not equal to zero simply also means that the expectation value, vacuum expectation value of this meson field is non-zero either. Okay, and but it should be flavor symmetric, etc. pp. So the simplest one is just that it's a constant times the unit matrix in flavor space. And flavor space, just as a reminder, that counts up, down, and eventually strange. Okay, so and then we go to the nonlinear realization of these meson fields. Well, this is just nothing else but polar coordinates in matrix space. So we have a radius and we have an angle, and the angle, that's the so-called chiral field. It's a unitary 2x2 matrix, and that contains the pion field. And tau here, these are just the Pauli matrices to produce a unitary matrix in here, and meson fields carry a dimension energy. So therefore, we need a dimensionful quantity, call it F, to make the argument of the exponent flavorless, dimensionless. Okay, so and then the simplest case, which is Lorentz invariant and which is flavor invariant, just has two derivatives on this chiral field, d mu Decker. And if you expand it, you just get the ordinary kinetic term for the pions. So there are three of them, pi plus minus and pi 0, and these three are combined in that vector. Okay, and if you go to the next order in there, the next order would have 4 pions, so that would contribute to pion-pion scattering. And it would also be proportional to 1 over this constant f squared. Therefore, we have seen earlier that the coefficient of the 4th order term should scale like 1 over nc. So this coupling or this scale in here should be of the order square root of nc. Okay, and so and usually you get a number for that parameter, the pion decay constant, when you add electron weak gauge fields to that and let the pion decay into a muon and a corresponding neutrino and get it from the lifetime of the pion. Okay, finally, so we have established a meson theory, and we now want to construct a soliton in that theory and try to find baryon or determine or predict baryon properties from that soliton. Okay. Well, we're not here at the soliton yet. Okay, there's a few obstacles from a mathematical point of view. So if you go back to, for example, to the kink, a soliton in 1+1 dimension, you actually see that the derivative and the potential terms in the energies, they balance to stabilize the static soliton. And so far, we don't even have a potential term for the effective meson theory. But of course, I mentioned it already, these quarks are not exactly massless, but have a non-zero explicit chiral symmetry breaking, and that is reflected by a small but non-zero pion mass. And you can write down that in terms of the chiral field simply as a trace u plus u dagger minus 2. And that gives you, in the leading order and the expansion on the pion strength of the pion field, just a mass term. So let's assume you took these two terms from the Lagrangian, you built an energy functional, and you had succeeded in finding a solution that minimizes that functional. Then you can scale that functional, or more precise, you can scale the argument of the function in there, and you can write that into the resulting energy functional as a sum of two terms that come from the energy of the assumed solution and scale like 1 over s or 1 over s cubed. And then it's immediately obvious that this object is not stable. Okay, so you can there's no single non-zero finite value of s for which this is minimal. So this thing doesn't have a soliton, so that's just Deriv's theorem. So for that reason, Sturm added his famous Sturm term, which is quartic in the derivatives. Okay, so and therefore, if you perform the same calculation as above with the scaling, you get a term that's rising linearly with s, and therefore, combining these three terms, you really find a stable quantity in there. So this thing has 4 derivatives, but it's written in terms of a commutator of derivatives. So therefore, it's actually only quadratic in time derivatives. That will make a quantization easier later on. Okay, so but it's quartic not only in the derivative, but also quartic in the pion field. And if you write it out, you get one f pion decay constant for each of these alphas in there. And therefore, the coefficient here is 1 over f squared and e Sturm squared. Again, this thing should scale like 1 over nc. F 1 over f to the power of 4 scales like nc by its squared by itself. So the Sturm constant in there should scale like the inverse square root of nc. Okay, so yeah, so now we can write down an ansatz in here. That's the so-called Hedgehog ansatz, simply because these vector fields that represent the pion, so representing the isospin, they point in radial direction out of the sphere. Okay, so just like the digits of a hedgehog. Okay, and then this thing was already known to Pauli. Okay, and this quantity f of r, that's called the chiral angle. You substitute that into the Lagrangian you get a nice energy functional. And if you're smart enough to find a dimensionless variable in there, you can scale them out, except of the pion mass term in there. But as I already argued, that has a minor effect only. So the first thing that you observe is that the coefficient in here has a square root of nc there, 1 over a square root of nc down there. So it really scales like nc. So that's fine. That's what you wanted to have. Okay. And you can also write down the stationary condition from that by just minimizing that functional in there. Gives you second order differential equation for the chiral angle. Imposing certain boundary conditions that I will argue for in a minute. You can find a solution which is numerically, which is actually quite boring. Okay, it's just more or less linear decreases with the radial distance from pi to 0. And that actually was great, that the actual solution is so close to a line was Sturm advantage, because he did not have the computer power to solve that equation. So he just assumed a straight line and just performed a variational calculation with a position where the line cuts 0. Okay, so, and as I already said, if the pion mass here is ignored, every parameter dependence scales out, and you can find a generic number for the classical energy. So it's just 23 times pi times a combination of the coupling of the constants in the model. And this would, if you want to match the proton mass with that, you would read a rather large Skyrm constant, which is not really realistic from pion scattering. Okay, so if you go back to this bosonized NJA model, you can actually write down the expectation value of the baryon current, and you will find that it has a gradient expansion or a derivative expansion, and that the leading term is nothing else but the baryon number current. So it's a topological charge, and this simply counts how often you cover the target space, which is SGSB isospace of the pions, once you covered the coordinate space once. Okay, so and if you substitute the Hedgehog ansatz in this expression for the topological charge, which now turns out to be the baryon number charge, you could just get the difference of the chiral angle at 0 and infinity modulo a factor of 1 over pi, and that's why we have this boundary condition 0 and infinity. And there is actually a BPS identity arising from that, BPS, Bolívar, Brasson, Sommerfeld, they wrote down BPS theories in the 70s, so that came actually after Skyrm, but Skyrm already knew about the particular bound in his theory. You can simply rewrite the energy functional for the Skyrm model in terms of a positive definite quantity and the baryon number current. Okay, so and that gives a lower bound, which actually is significantly less than what the numerical result gave. So therefore, the question is the Skyrmion with the Hedgehog ansatz really the actual solution? But for the time being, let's stick with that. And let me just mention a few calculations with higher baryon numbers. So the first thing, of course, you would do is to just take the chiral angle at 0 to be twice as large. But when you then calculate the energy, you get 3 times the baryon number 1 energy. So that thing is certainly unbound. You can double the winding in the azimuthal angle. That is significantly lower in energy, but still unbound. When you then go to the lattice and not only take a radial function in the exponent, but a function that depends on both the radius as well as the polar angle, then you really get something that's bound. Okay, at least classically. Okay, so but this was the status of whatever 20 and more years ago. And in the meantime, people have done sophisticated lattice calculations and found solutions with baryon numbers or binding numbers up to 100. Okay, so these are some equipotential lines for different baryon densities. Okay, so for B equals 108 or 104 and so on and so forth. Okay, so we need to generate baryon states because the Hedgehog by itself does not have spin or so. Okay, so we would need time-dependent configurations. Solutions of that kind are not known to date. And what we actually do is we consider approximations, and this is called the collective coordinate approximation. So just look at it in ordinary quantum mechanics. If you had a potential that's radially symmetric, and you just rotate about a particular axis around the potential, about the minimum, okay? What D is some rotation matrix in there. And if these rotations are slow enough or adiabatic, that wouldn't take much energy, and you can write down a Lagrangian in terms of the Euler angle for this rotation, and you can quantize that object in there and find the rotational spectrum, which is more or less the same as you would get in an ordinary perturbative treatment of the angular barrier in quantum mechanics. Okay, we do the same thing in here. We introduce collective rotations for, in this time, in isospace or in flavor. And actually that can be also written as a rotation in coordinate space, which tells us that the isospin and coordinate rotations are equivalent. But similar to this quantum mechanical example, we write down Lagrangian for the angle velocities that come out in here. which are nothing else but the time derivatives of these rotations. And the coefficient of the kinetic term is nothing else but the moment of inertia. And the moment of inertia can be written by, or can be obtained by simply substituting in the Hedgehog solution again. And you find a functional that you can evaluate numerically and get a number out of that. Okay, and well, I'm not going to discuss the details of the way it actually goes. Is that you can get a rotational spectrum, just similar to what we had in that quantum example. And you can write down an SU2 operator simply as a conjugate operator to the angular velocities. They will have ordinary SU2 commutation relations. And it turns out that, and you can then calculate or construct the isospin as a Noether charge for the flavor transformation, which is nothing else but a commutator of the chiral field and the flavor generator tau halves, and that can be related to the time derivative of the Hedgehog. And what you will see is then that the isospin is nothing else but rotation of that SU2 operator J, which in turn turns out to be the spin operator. So from that, we see that actually the absolute value of the isospin and the spin are identically. That's exactly what we have for the proton and the neutron. They have isospin and spin 1/2. And then there are a few other calculations that you can do from the Wigner-Ecker theorem. For example, you can calculate, it's hidden very early, matrix elements of this rotation matrix D between nucleon states, for example. And then we can make the very first prediction as the mass difference between the delta and the neutron, and it's nothing else but rotational excitation going with 1 over alpha squared. Didn't say that, but alpha itself is order NC, so this is actually an order 1 over NC correction. Yeah. You go on and calculate various baryon properties by looking at the symmetry currents that, again, you can express in terms of the chiral field. Substitute the Hedgehog ansatz in there and get an expression for these symmetry currents in terms of radial functions that are given in terms of the radial dependence of the chiral angle, and these flavor quantities like rotation matrices or angular velocities. And yeah, then you can, for example, calculate the magnetic moment of a neutron, which is then nothing else but an integral over such radial functions. And you get two values for that, for the proton and for the neutron. And well, these are just some data that you get, or results that you get from that calculations. These are not too good, I have to admit, but after all, we are just looking at the simplest of all these models. Okay, so I should not go too much detail, but we have to do the same thing now for 3 flavors. There are 2 interesting things we have to look at. The first one is that we have to look at flavor symmetry breaking. So this strange quark mass is not really small. On the meson side, that simply means that the kaon mass is not small, and we get some flavor symmetry breaking. But technically, the more interesting thing is that you have to add the Wess-Zumino term, which is a non-local term. It's defined on a 5-dimensional manifold, and the 5-dimensional manifold has a boundary, and that boundary is the ordinary Minkowski space. Okay, so for 2 flavors in SU2, that would not survive because you need 5 linearly independent generators in here, but in SU2 you only have 3. Okay, so on the meson side, that describes reactions like pion for 2 pions scattering into 3 kaons, and that's how Wess and Zumino wrote down that term earlier, and later Witten described or discussed the topological properties thereof. Okay, so and also it's able to, after gauging with electromagnetism, describe the anomalous pi0 decay in there. So we now do the same thing as before, only that our flavor rotations are now in SU3. Okay, so and we embed the original Hedgehog that we have already, and we have already this f of r in there, and do simply the same calculations in there. We get a Lagrange function, which now has two moments of inertia, one for the ordinary spatial rotations and the other for rotations into a strangeness degree of freedom. And in addition, there is a contribution from the Wess-Zumino term that comes with the eighth of these 8 angular velocities. And that's somehow interesting because the lambda 8, I didn't write it down, but the lambda 8 commutes with that embedding in here. So from any local term, you could not get a contribution involving lambda 8. But the non-local structure of this Wess-Zumino term makes that possible. And when we then go to the same calculation as before, we find generators as the conjugate momenta to the angular velocity. The 8th generator is just the contribution from the Wess-Zumino term in there, and that gives us a constraint. Okay, so for n equals 3, it just says that what's called the right hypercharge must be equal to 1. Okay, so it's no longer a dynamic quantity, it's a constraint, and this constraint tells us actually which SU3 representations for the baryons are actually allowed. Okay. And let me skip the details in here, but it not only does it say something about the SU3 allowed representations, it also tells us that the J3 value, which is this protection quantum number of the spin, must be half integer. Okay, so in the SU3 version, the 2 version, we actually did not say, did not have any information on whether J was half integer or integer. So it could also describe mesons. But now if we go to SU3, the Wess-Zumino term tells us that we really have to consider fermions. Okay, so and that's what's now coming up. Okay, so these allowed representations, the low ones, they are actually the octet and the decuplet. The octet contains the ordinary proton and neutron, but also the sigmas and the lambda and the xi's, and they all have spin 1/2. And the decuplet, these pictures are also well known from the quark models. The decuplet contains the thin low-lying spin 3/2 baryons. But also higher dimensional representations are possible. They all satisfy those constraints, like, for example, the anti-10 or 10 bar or the 27. Okay, so they all have YR equals to 1. In there, of course, what I'm displaying here is the representation concerning for the left generators that are obtained from the rotation of the right generators. Okay, so they must be the same multiplets, but they are not restricted to y equals 1. Okay, so and if we add flavor symmetry breaking, we get additional terms that are not only dependent on the angular velocities, but explicitly on the collective coordinates A. And once they are introduced, we will actually see that the nucleon state is not a pure octet state, but it has an admixture from the nucleon in the 10 bar or the nucleon in the 27 in there. But also interestingly, this additional representations, they have states that cannot be described as ordinary 3 quark states. Okay, so for example, the top red line here in the 10 bar must have U or 2 U's, 2 downs, and an anti-strange. So this has 5 quarks altogether. So, and these are the famous pentaquarks. Okay, so let me just sketch a few of the numerical results. They are not necessarily coming from the SCER model, but from some refinements of the SCER model. But I want to show it to you that they indeed give very sensible results. For example, for the mass differences of all the octet and decuplet states with respect to the nucleon. Okay, so they're all within 20 or less MeV from the experimental data. Similarly, for the magnetic moments that are also right in terms of ratios of the given baryon magnetic moment and the proton one, There are a few exceptions in here, for example, the size 0, which is still a bit off. That can also be improved, but that's a technique where you have to include flavor symmetry on the basis of the soliton, which has not been done in here. We have only taken one soliton. You can answer interesting questions on the strangeness content of the nucleon, so meaning there are quark, anti-quark pairs inside the nucleon where the quark is a strange quark. Okay, so I'm already more or less finished with my 1 hour. So out of the many things I'm going to skip is the details of the meson baryon scattering. Let me just mention one thing which I indicated earlier. So what we're actually doing is we're looking at small amplitude fluctuations about the soliton and get some harmonic equations for these fluctuations. And yeah, once we do that, we get some kind of a Schrödinger equation for these fluctuations. And there is no solution which has a negative frequency squared in that Schrödinger equation, which actually means that this hedgehog is at least a local minimum. Okay, so I said earlier that the hedgehog would exceed that BPS bound by about 20%, so which might suggest there is another solution. Certainly, there's no other solution in the close vicinity of configuration space. Okay, so and in the meantime, there have also been lattice calculations which show that indeed the hedgehog is the actual minimum. Okay, so I'm skipping that thing in here. I'm also skipping the part on vector meson extension, even though these results, numerical results showed earlier in here, come from such a vector meson model. Okay, so then things get a little bit messy. Okay, so the energy functional becomes large. You have to look for additional excited fields or induced fields once you do the collective coordinate rotation, getting worse for free flavors. So these were calculations that were even the result doesn't fit on a few pages. And so to say it with Billy Joel, that were calculations that I could do when I wore a younger man's clothes. Okay, so there are certain improvements. For example, the radii become larger and things like that. We are also able to really get a non-zero result for the neutron-proton mass difference once we include the appropriate mass difference for up and down quarks. Okay, so I was brief here on a number of topics, and there are other topics that I didn't cover at all. Okay, so and I will just mention them instead of a conclusion. So I only mentioned the magnetic moments. These are just the zero momentum pieces of certain nucleon form factors. There is a whole discussion on calculating the momentum part of these form factors. There are actually NC constraints on the flavor multiplets. So that constraint for spin 1/2 I actually gave for NC equals 3, but the whole discussion started with NC being arbitrary or at least being odd. So there are a number of such constraints that come up, and they are very interesting. I only briefly mentioned flavor symmetry breaking, and I mentioned that in the context of the energy eigenvalues, but it can also be discussed in the content of the baryon collective coordinate wave functions when you vary the kaon mass in the effective meson theory from taking the value of the pion mass and let it grow now almost to infinity. The opposite way is also possible, where you start with a scenario where the kaon mass is large and then tune it down to the pion. And together with these NC constraints, you will actually see that these two limits indeed match, but that's anything but trivial. Okay, so I didn't talk at all about heavy baryons. So that are baryons that contained charm and bottom quarks. Certainly the chiral symmetry is not a good symmetry to build the effective meson theory. So rather you need to look at the spin flavor symmetry and how to couple that to the pions and other low mass mesons. I didn't talk about the extension of having quarks in these solitons. So these are not really the QCD quarks, some chiral quarks like in the NGA model. But once you've got those guys, you can look at nuclear and structure function, make prediction about that. I mentioned the existence of pentaquarks, but did not talk about all the studies in there, in particular, all the garbage that has been published on the width of these pentaquarks. Did not talk about systems, or almost not talk about systems with large barrier numbers. You can make predictions about the nuclear potential, but even can go to dense matter the scenarios. There's a very complicated thing in this context, which is the quantum corrections. They are certainly important, but nobody really knows how to deal with them in the context of these chiral models, simply because these chiral models are not renormalizable in a perturbative sense. Okay, so I hope it at least gave the impression that a lot of things can be done with just a single soliton, the skyrmion, and small extensions thereof. Then it only remains me to thank you for your attention during this an hour and a little bit more.
Thank you very much, Professor Veiger. We enjoy your presentation. Thank you very much. At the moment, I cannot see any questions. If anybody has a question.
Can I ask a question?
Yes, please.
Okay, so you mentioned that this skyrmion model is used to predict some results for the scattering of mesons on nucleons.
Yep.
What about collisions between nucleons, like proton-neutron collision? Can the skyrmion model predict correctly the results of low energy phenomenology of such collisions?
Yes, what they're actually doing is you can, when you go to certain configurations with barrier number 2, you can calculate or at least extract from the energy functional the potentials for these nucleon configurations. Okay, so and then these potentials are often compared to effective potentials that are extracted from data like the bond potential. What else is there? There's the not Urbana. What is this suburb of Chicago? I forgot. Okay, so the bond potential and a few others in there. Okay, so and that at least for large radii of these potentials that works well. For intermediate radii, it doesn't work that well. There's what's missing in there is something like the intermediate range attraction. Okay, so but there are certain extensions of the Skr model where you also include a scalar field that makes up for that intermediate range attraction, and then you also get that to work. And that small radii, you get the repulsions from the omega meson and the rho meson exchanges. And once you take those models which have these rho and omega mesons built in, you also get reasonable agreements with the potentials in that regime.
Yes, thank you.
Okay, thank you very much. Professor, I have a question about your presentation. Is there any specific reason that why we use the Skr model for baryon models? I mean, why we use only Skr models?
No, we use other models. Okay, so the Skr model is the simplest out of that.
Oh, is that because of they have a spin?
No, but actually the skyrmion by itself does not have a spin. The skyrmion by itself is a superposition of many spins. Or no, many isospins, but zero spin. Right? So we still have to generate those states, and that's where the collective coordinate quantization builds in. So there are essentially just to build or to write down a quantum theory for these skyrmions.
Okay, thank you.
Okay, Herbert, it doesn't seem like we have more questions from the audience. Please, if you're welcome to raise your hand, we can give you the right to speak if you prefer to express your question verbally.
Maybe one more question. If
Yeah,
possible.
please.
Okay, the question is not actually directly related to square model, but the question is that it's commonly known that the neutron is unstable, but of course it's not unstable because of the weak interactions, and weak interactions definitely is not a part of the square model. But I'm wondering if there is any possibility to maybe phenomenologically add some additional term to the model so that to somehow take into regard the instability of neutrons due to the weak interactions.
Well, the decay of the neutron is actually governed by the axial coupling to the electroweak gauge fields. Oh no, it's a combination of axial and vector coupling, but the vector coupling at zero momentum transfer is fixed by the charge, but the axial coupling at zero momentum transfer, that's a model prediction. Okay, so and from that model prediction you can actually do, so you can calculate the transition matrix element of the axial current between a proton and a neutron. Okay, and that's the so-called GA, the axial charge. It comes out a little bit on the low side in these soliton models, but that calculation can be done.
Okay, thank you.
Thank you. Then Herbert, thank you very much on behalf of all the participants for a very interesting lecture. I think we all learned a lot. And let me maybe conclude with the advertising for the last lecture in this series, which will be next Wednesday, and it will be back at 2 o'clock instead of 2:15. Today was the exception, so no rule without exception. But next week it will be again at 2 o'clock. Yeah. So Herbert, thank you very much.
Welcome.
Professor Malome, thank you very much for being with us again today. We'll hope to see you again next week. And Daniel, thank you very much for putting it all together. Thank you very much. And have a good afternoon.
Okay.
Thank you.
Ciao.
Bye. Bye-bye.
Bye-bye. Goodbye.